think I'm ready.
Hi everyone. So can everyone see my slides?
Yes.
Okay, thank you. Yeah, so my name's Timothy Peter. I am working at KSMC, do collaboration, and also I'm a master's student here at KSIMUKO. So today I'm gonna talk about the difference in quasi-experimental design. So I'm gonna talk about the introduction to the quasi-experimental studies, and also I'm going to show some case studies that use quasi-experimental studies, and I'm going to talk about the difference for the quasi-experimental study, and I'm going to show example live coding in R on how to do that. So starting with the introduction is, so as we have similarly to the experimental trials, the clinical trial, the quasi-experimental design also aims to establish cause and effect relationship between the exposure and the outcome for intervention. So, but the thing about this is it lacks random assignments. So people used to call it the non-randomized trial, the pre-post intervention studies, and the other names. So the clinical trial, the randomized control trial is being considered to have the highest level of credibility because it assesses causality because it have random assignments to the participants. So in medical or epidemiology, so we often put in intervention, or trigger the development and the implementation of intervention if there is a rise in the rate above the mean or normal or norm. So if you see maybe we have abnormal increase, maybe death in a certain group of population, or the cases of disease they rise above the mean, above the normal range, or the things behave above the normal, is where we have to trigger or to put the intervention towards that to solve that. So so as you say, in the quasi-experimental design, we don't have randomization. So we have several reasons why we don't randomize patients or participants. So some of the reason is the ethical consideration. So maybe if the treatment is gonna help patients to get better or save their life, and maybe you don't give them treatment because of the research purpose, that is not gonna be ethical, valid or consider ethical. So it's like a play with people's life. So sometimes you have to choose quasi-experimental design to study to do a study, and all patients may benefit from the study. So some also other reason is difficult of randomizing subjects. So you can have difficult to randomize subjects because patients may be randomized to a certain drug or certain intervention, but they cannot do that for some reasons, maybe social, cultural, or side effects to that. So maybe, yeah, it can make them not, it can make randomization difficult. Another reason why we don't randomize patient is difficult to randomize by location or geographical places, like wards. So maybe we randomize to certain wards, maybe you can migrate or move to the another ward, then you'll be maybe allocated to the wrong blocks or wrong allocation. So also we can have the population with a available small sample size, and then it makes us difficult to randomize patient into those intervention group and control group. So in a typology or stream of epidemiological studies, we have experimental studies and observational studies. So randomized control trial and the quasi-experimental design, they are all experimental studies. And the other cross-sectional studies, cohort T studies, case control study, and ecological study, they follow in observational studies. So quasi-experimental studies like time series are one of the experimental studies. So this is the hierarchy of experimental of the quasi-experimental studies specifically. So number A is a quasi-experimental design without control group. So you have only post-test only, so you have to observe you see you observe, you see the outcome, then you observe what is gonna the intervention, then observe what is gonna happen. You put the intervention, then observe what is gonna happen to that group. I'm not gonna talk so much about this because I don't have many of them. I don't have valid examples for them. I'm just gonna talk real quick on that hierarchy. Also, we have quasi-experimental design that use a control group, but not pre-test. This is the only post-test, and then you use only control group after giving treatment. Then you have to start them. Also, the quasi-experimental design that use control group and the pre-test. So you use both control and pre-test, but you don't follow them over time. So number D is the interrupted time series design. So here we have multiple pre-test and post-test observation, and then they are spaced at equal interval of time. So if you follow this participant, your patient for 10 years, then you have to maybe we can place intervention at the mid of the 10 years and start those who have intervention and those who doesn't have intervention, and observe the outcome that you have to observe. And the number D have been considered as the best in the hierarchy of quasi-experimental study. The time series study has been the best study design in the list of the quasi-experimental design compared to the other categories from A to D. Number D is the best one. So this is the case study. This is an example of study that we did here at KSMC that used the quasi-experimental study. So that study used where we are planned to, we are aimed to see what are the predictor of safe repackaging of antiretroviral therapy for HIV patient in northern Tanzania. So the goal of this study was to observe if patient, what are the predictor of patient they're gonna repack, like remove the original package of medication and put the another package from the medication they receive from the pharmacy. So maybe patient do that maybe for the reason, maybe things like stigma, or maybe they are convenient to carry it without the original box. Maybe they are big. Yeah, maybe people they want to see them with maybe with the ART medication. So we have to see what are the predictors of repackaging. So before we see that predictor, we have to see if they repack or not. So the quasi-experimental design here use the category A, whereby you observe and then you see the outcome, then you observe again. So the criteria for repackaging was to if patient was repacking the medication at least twice. So somebody in the pharmacy was there, like the medication was dispensed to the patient, and then they observe if patient to repack it or not. And then once patient come back again on the second clinic, and the clinic, then there is a consecutive observation to see if the patient repack or not. So this is a quasi-experimental design. As you see, participants are not randomly assigned for repackaging or not repackaging. Instead, the group based on the observations. And later, they came to the clinic and asked the only ones if and they have to report if they have ever repacked their medication. So by asking them by self-reporting it was one of the aim to do the sensitivity analysis to see if the observed pattern is the same as the self-reported. So if somebody else come to do the same project, it doesn't have maybe to observe, maybe they can just ask patient. And we found the sensitivity was higher. So yeah, from the analysis we found it was high, and then we decide that we don't have to observe patients. We can just ask them if you have ever repacked your medication or not. So it could be like a message to other people, like you want to do behavioral studies like this one. It was from the SBAS studies. Yeah. So this is another case study. Yeah, from our team from the TBI studies here at KSMC Emergency Medicine, whereby these studies aim to evaluate the effectiveness of clinical practice guideline for acute management of traumatic brain injury at a regional referral hospital in Tanzania, which is KSMC. So this study was aimed to evaluate if the EMD CPG is going to make changes in TBI poor recovery rates, monthly TBI poor recovery rates. So TBI registry was there since 2013, and then on July 2016, the TBI CPG was implemented. So we can see the patient with poor recovery rate was increasing at increasing rate until July 2016. And immediately after TBI CPG was implemented, then there is a rapid fall of TBI poor recovery. So you can see the TBI poor recovery, the CPG was worked better in reducing the number of TBI poor recovery. So we did the same analysis for the long data, because as you can see here, there is no like equal interval over time. So the CPG was implemented, the patient was followed from 2014, and the intervention was placed on 2016. And then the effect was only evaluated after in 1 year, 2017. But here, where the CPG was from 2013, and then the CPG was kept in 2016 here, but we tried to evaluate it at 9 months because there are some training here for the healthcare providers. And then from 2017, we evaluate this from 2017 to 2022 so that we can have longer interval of time and to study it and to have like equal intervals of evaluating this. So as we can see also, the TBI, this and then and here we didn't study the poor recovery rate. We studied the TBI mortality rate. As we can see here, there is autocorrelation. This is a monthly TBI deaths. So you can see there is areas with high deaths, there is months with high deaths, there is months with low deaths of TBI. Like at the end of the month, there is higher deaths from TBI. So as we can see here, these dots are the deaths. So we can see the deaths for TBI from TBI patient are still decreasing from 2013 up to the end. But immediately after CPG implementation, there is a rapid drop here. You can see that the deaths are still decreasing up to 2022. But the green line here is the counterfactual line, which show that without CPG, if CPG could not be placed at the emergency department, the deaths could be higher, could continue to behave in this pattern, like they could increase. So the gap we see here is the counterfactual effect that the CPG reduce the mortality rate for TBI patients. Yeah, so, and this is one like
Timon,
yes, Joel.
can you go back to the figure? Yes.
Yeah.
No. For the new one, for the new data. Yeah. So I just wanted to reiterate one thing that Timon touched on the introduction. So these methods, the quasi-experimental methods, they are really useful in a few situations where you cannot randomize patients. Timon told us that, but specifically, I want to talk about this example. So, if you are implementing a new CPG in your hospital, it's not ethical for you to provide good quality of care for a group of patients and not the same quality of care for the other group. So in this situation, it's not ethical for you to randomize the patients. And that's why we use this sort of like retrospective before and after analysis. So retrospective and then prospective analysis in this quasi-experimental design to get the sense of if the intervention was successful or not, right? So this is really, really important. And even though it's not a randomized design, randomized experimental design, it still holds a lot of power to detect the impact of interventions. So it's a technical design that we should always consider. And Timothy is showing this great figure here for, I think this is for Vivian's work, right, Timothy?
Yeah.
Yeah. So Sister Vivian's PhD work, yeah, which Timothy is leading the analysis. That's all I wanted to say. Thank you, Timothy.
Yeah, thank you, Joel, for highlighting that. Yeah. So yeah, because we could be able to, as Joel said, we could be able to randomize patient that this is an ethical, that this is gonna be treated with CPG and this is gonna not treated with CPG. Then we do use time to follow them when they see what happened after the CPG implemented at the KSMC emergency department. So this these autocorrelation plots can be, so I want to take you to the where difference in difference lies come. So these autocorrelation plots, they are one of the way to validate or to see how does the time series behave over time. So we can see from 2013 to 2022, we have observed the TBI deaths. So the TBI deaths ranging from 2 deaths to 10 per month. So there is places where we have two higher deaths, and there is time where we have low deaths as we study this over time. So also there is a trend. There is sometimes we can see this trend here. There is sometimes where they have deaths from 2013, they are highs and they are high, and then you can see they are dropping over time, they are going down to zero. So seasonal also, this is the seasonality of the deaths. So there are times that there is higher deaths, there is also time, there is also season that there is low deaths. So there is, like, maybe you can see here, maybe at the beginning of the month or end of the month of the year, there is higher deaths. You can see at the middle of the year. So there is season with higher deaths and there is season with low deaths. So, and this is the randomness. This is how the observed can be predicted to to show the randomness. So there is areas where the deaths can happen also in random in nature. So randomly can have higher deaths or can have low deaths. So this is the autocorrelation plot to show how your outcome, because I did it monthly, so you can see how these things behave, how we have this outcome behave over time. Yeah, so why difference in difference? So the difference in difference is a technique, is a statistical technique used in econometric, also in quantitative research, and it used to mimic an experimental research design. Not only in quasi-experimental study, it can also used in a in a randomized control trial, like the practice we have at KSMC. You can do also difference in difference by using the observed data. So this is used to see, to test if the intervention we have is the one that caused the effect we see. So we do it by comparing average change over time in the outcome variable for the treatment group and the average change over time for the control group. Like here, we'll do the average change over mortality rate for the treatment group, which is this in green, and the control group, which is this in purple. So it is intended to mitigate or to control for the extraneous factors. Like extraneous factors here is a confounders variable and the selection bias. So the thing here we have to take care is the difference require at least require data measured from treatment group at least 2 or more different time period. So you need 2, like here, from the control group, you need 2 time period, and from the treatment group, you need 2 time period, which you choose them randomly, but you have to consider the symmetrical purpose. So I'm gonna talk about that. So this is the validation of the why we do difference in difference. So sometimes difference in difference is needed because of validity, also internal validity of the findings. So number one is reason why we did that. There is ambiguous temporal relationship or temporal precedence. So there is a lack of clarity that whether intervention occurred before outcome. Maybe the poor mortality started to decrease before even the CPG. Like you can see here, there is TBI mortality started also to decrease, as you can see, before the CPG. So the temporal relationship can be assessed by this analysis of difference in difference, because you can see also the mortality was still decreased even before the CPG. So the reason is the selection. So you can see the selection bias. You can select participants who have good recovery or poor recovery. Also maturation. There is natural occurring changes over time. by nature, which is confused with a treatment effect. Also regression from the mean. So when we select a patient or participant with extreme scores, they can regress from the mean, regardless the kind of regression you are doing. We use the linear regression, but also if you use the other kind of regression, you can also see this. You can see the effect, which is not true. Maybe you choose the extreme values or the extreme score or some group of patients which may have the extreme chances of maybe dying or what or having or surviving. So attrition also we can lose respondents that can produce artificial artifactual effects, which can produce the good, can show the effectiveness very well or wrongly. So testing also, exposure of a test can affect score on subsequent exposure to that test. So there are some pre-test and post-test, like somebody can they can test those patients like twice, not in this fashion of time series, also for the other type of quasi-experimental studies. You can observe the patients like twice, like the way I show in a repackaging. You can observe them first time, you can observe patient the second time, then first test, then you can affect the second test in one way or another. So instrumentation, the instrument may be used to test the efficacy or the effectiveness may change over time. Also, interactiveness effect. The impact of an intervention may depend on the level of another intervention. So like let's say, for example, for our practice trial in KSMC, that is the another trial, which is not the QUAS, it is a randomized trial whereby we try to observe if the injury patient receiving counseling, they can lower their consequences related to alcohol. So the counseling, it's having themselves, the counsel themselves, they have levels. There is inferiority and the superiority level of counseling. So the intervention as intervention, they may depend on the level of another intervention, and then they can affect the outcome. Maybe you have to find a way you can maybe present for the inferior or an inferior effects. And then that's why we need difference in difference. So let me run you quickly on how we do the difference in difference. So you have to subset the data. You have to create the data set that you can work on R. So like here, I group the I select the variables that I can work on: the admission, number of patients admitted per month, deaths, year, and the intervention. The intervention means the year before 2016 July and the year after 2016 July. And then I sum the total number of admission and also sum the total number of deaths, so that I can calculate number of deaths per patient to arrive at the EMD. And then I record this, then the intervention variables, the one that come after July 2016, they be called as the after CPG, and then those come before, they've been called before CPG. So this is how we create the treatment variable. So this variable that is going to be used to do the difference in difference analysis, you create the variable arbitrary, because you remember here the CPG intervention occur at the July 2016. So you have to choose from July 2016, you have to choose like 1 month, 1 year later, and 1 year back. You can't choose like 2 years later, 1 year, 2 years back from the intervention. You have to choose like 1 year after intervention and 2 year before intervention. Sorry, 1 year after intervention and 1 year before intervention. And from that, you have to choose the control and treatment groups from those years. So as you can see here, what I did is I did it with the help of Cyrus. So I choose, because the intervention was done on July 2016, and then I choose to take patients from 2015. 1 year from 2016 is a 2015. So I took patients from 2015 January to July to June 2015 to call them as zero. That means they are as a control group. And from June to December, from year June to December 2015, I call them as one, which is a treatment group. So this is the 1 year before intervention. And then I did the 1 year after intervention. I did the same. So remember the intervention occurred the June 2016, sorry, July 2016. Then we have to choose one, we have to choose 1 year after 2016. Then it's 2017, June. So I choose those participants who arrive from January, from June 2017 up to, yeah, from June 2017 to call them zero. Sorry, from January 2017 to June 2017 to call them zero. And from June 2017 to December 2017 to call them one as a treatment group. So one is a treatment group, zero is a control group, but two different should not be. Remember, when you choose this, you should not choose participants that follow exactly at that time of intervention. You should skip that year of intervention, the year of 2016. So, and then you have to see, maybe you can tabulate to see how many you have control and treatment group. And then from that, you have to correlate it to regress it against the mortality rate. So from my data, I have the mortality rate, which I did the number of deaths per month divided by number of admissions per month. And then I create a new variable known as DID, whereby I did the new, I did another variable, which we call them the DID. So the DID was the interaction, was the multiplication between time and the treatment. So after I did that, then I consider it as a factor variable, and then I did the linear regression. So before doing the linear regression, I have to define the start and end date so that I can subset and work only from the subset of the data set that I choose. Remember that the data set is the data set we have from 2013 to 2022, and then I choose from 2015 to 2017. So the chosen dates are from 2015 to 2017. Then I have to work only with this data to do the difference in difference analysis. Then I subset this one, and then I did the linear regression, whereby my outcome is going to be the monthly mortality rate as a function of time interacted with the treatment. And then after I did that, this is the linear regression results. So forget about this estimated the Poisson regression result. I didn't show you the codes towards that, but what we did, we just did the Poisson regression to see the monthly effect of the CPG intervention. So we did that, and we see like those patients who treated with the CPG intervention, they have lower mortality rate by 0.76 compared to those who treated without CPG intervention. But that was not significant. And over time, after 1 month increase, the CPG, the mortality rate decreased by 1%, and it was significant. That as time goes, patient benefit from the mortality rate decrease. So the thing I did for difference in difference was to prove this 0.76 effect we see here. So consider the DID estimate here. So as you can see, we have negative difference in difference estimate, which show that negative 0.018, which show like the TBI mortality rate is decreasing. The negative estimate indicated decreasing. The positive is indicating like it's increasing. And the non-significant p-value shows that the effect we see here is not due to the CPG intervention. It was due to the other things like infrastructure changes, human resource, and the other frailty that we could take into account on your analysis. Yeah, so the take-home message here is the p-value from the DID estimate. That is the one that's gonna tell you if the effectiveness you see from from your trial was due to the intervention that you have made, or it was due to other things which was not the intervention. Yeah, thank you. Also, sorry, let me talk about a little bit about this one. So this one was the prior study to this one that me and Joao was talking about. So this one was the study that was done and published prior to that one. So this one, other author Joao, Catherine, and the others, they did that and they use ARIMA, so autoregressive moving average. So as you can see, there is a change in slope, and this difference here, it's corresponding to this graph here, this one. So we can see there is a change in slope, like there is a negative change in slope that after intervention. So it's true, that is also depicted from the graph. And also you can see the DID estimate. So as you can see here, there is a decrease in poor outcome as time goes. So, but the p-value from the difference in different estimates is marginal significant. It may be true at that time, it is a long time ago, 2017, we didn't have a lot of infrastructure, we didn't have human resources enough. Maybe the observed decrease in mortality rate was due to the CPG. That's why we have like a marginal or closer to significant DID estimates that it almost support that the effectiveness we see here was due to the CPG intervention. But the current one doesn't support that because we have a lot of things that have already happened at the KSMC emergency department. Yeah, thank you. Yeah.
Thank you, Timo, for the presentation. I wanted to start by asking you a question for the DID that you showed at the end, that table. So just so I understand, you create the DID by selecting the time points before and after the intervention and calculating the difference, and you add that as a covariate to your model.
Yes.
Okay. And is it like a linear regression in this case, in the table below?
Yeah. Yeah. These are the linear regression results.
Okay. Hmm. And the outcome is the mortality rate, right? Or is
Yeah.
it the number of deaths?
It is mortality rate.
Okay. One
Yeah.
thing to consider, maybe I'm not sure if it's one thing that you used. Um, if you're using rate, maybe the distribution is not normal, right? It's gonna be um, probably negative binomial, I think.
Uh-huh. Yep.
So
Yeah, and
maybe one thing to go ahead, go ahead.
we didn't do like diagnostics tests to see the outcome if it is normal distributed or not, because
Yeah,
yeah, maybe I understand your concern. Maybe we could choose another model which is not linear, or maybe we could transform first the outcome to fit
yeah.
linear, right? Yeah.
Yeah, that's the only thing I would test before if you're preparing the manuscript because maybe by using the normal the linear no model they are assuming that you can have a negative rate, for instance, because of the normal distribution. While if since it's a rate, it cannot be negative for the rate of deaths at least. Or if you are using the actual counts, then you cannot have, for instance, the count that is not an integer. So just that's the only thing I would tell you to check if by using a different distribution would make more sense there. But otherwise, it looks great.
Yeah, also I was trying to I thought about it. I also asked Joao and Cyrus about if you have to choose another model for the linear regression because the difference is gonna tell us the average number. So
Mm,
another model that tell us more average number is only linear, is the one that tell us the on average the TBI death is this. So maybe if I could see, I could maybe choose the same linear regression and maybe observe if it is normally distributed or if it's negative binomial or having
hmm.
many, yeah, and if it's having, maybe I can try to transform it. Yeah.
Okay, sounds good.
Maybe I can stick with linear and then try to make sure it follow the diagnostics test is all of the
Sure.
diagnostics test. Yeah.
Mhm.
It's true. Yeah. Thank you for reminding me. I didn't do the diagnostics for this one. I just ran it.
No problem.
I've been a bad boy lately. I just ran without diagnostics. Okay, guys, welcome for questions, suggestions.
Yeah, so Timothy, thank you for a nice presentation. This is something that I was very looking forward to so I can understand. So if I understand, well, I see the model that is used here is the linear regression. And from what you're saying is that you could have used another regression, isn't it?
Yeah,
So the difference in difference um, is integrated here when you divided the time, like before intervention and after intervention. So the difference, I'm just trying to think, what's the difference between this and a normal linear regression, apart from the splitted time? Not sure if you're
mm,
getting the question.
yeah. Can you say it again?
Yeah, I'm saying, if I understood you well, you use the linear regression, right? And the outcome was mortality and that we have exposures. So one of the exposures is the splitted time, like before intervention and after intervention. So I'm thinking what's the difference between this one and just the normal linear regression?
It's just a linear regression. We just the variable that it is the treatment is the arbitrary variable that we create in to make sure that we separate we don't take to consideration the time when the intervention was done. It's just a normal linear regression that we've made that we used to do. It doesn't have any difference. As you can see here, just a simple linear regression. We just have to test if the this variable here is significant or not. That is our treat.
Aha, okay. So, but I see an intercept there, the DID, is that brought up with from the model? There's
The
a number in the
Go to
in
the
the
next
table.
slide, Timot.
this one.
No, the next
No,
one.
the
That's 17.
17th slide. Yeah, we have a DID estimate here. That's where I thought maybe it's a different thing from the normal linear equation.
Okay, that is
Mm,
the same regression.
Yeah, just
okay.
because we don't see that in the equation, Timot.
Yeah,
Maybe
Mm.
you
that's
should.
the
Yeah, maybe you could say plus the ID here. Okay.
yeah, maybe just copy the wrong line of code.
Yeah, maybe a copy line longer. Yeah, I think this variable here. This is the one.
Okay.
Yeah.
Yeah, yeah, and this is
Oh,
the
okay.
DID.
Okay,
Yeah.
so it's the same as the interaction. So the only thing that went in the model is the interaction. Okay,
Yeah.
go back to the
Interaction.
table. Yeah, so since you do the interaction, you have the individual coefficients, so for time and for treatment, and then they're both of them combined you get a DAD estimate. Okay.
Mhm.
And
Everything.
time is probably like a continuous variable, like sorry, like from the start of the study through the end, probably like a one, two, three integer, and then treatment's gonna be binary, I think, right? Before and after.
Yeah, is a before after
Yeah,
CPG.
I see. Nice.
Yeah, and the intercept is that the baseline time, baseline treatment, and the baseline DID.
Mm-hmm. Nice.
At the low. Yeah.
Okay.
Yeah.
And different from the model above, which is a segmented Poisson regression, this one gives you the raw value, so it's a direct increase, right, in the rate, the one below, while in the top it's an incidence rate ratio, which is a bit different, right? It's the rate between the comparison of between the two groups. So you gotta interpret the values above and below a little bit different because they are different models.
Yeah, this is the Poisson and this is the linear regression.
Mm-hmm.
Yeah, this was done to prove this one. Yeah, the ID estimate was done to prove this. If this estimate we see here,
Mm-hmm.
as we see those patients who are treated with the CPG, they benefit. They have low incidence rate ratio compared to the one who don't have treated with CPG. So we have to see this lower incidence rate ratio was due to CPG only or not. That's why we did this one by randomly choosing those participants prior the CPG and after CPG, by also make sure we are in a 1 year intervals. We don't have to go far from 26 from where the CPG was implemented.
Okay.
Yeah, it should be like the trick thing here was to choose this time. Like you should not go far from June 2016. Yeah, or go very closer when we can go and the time when CPG was implemented.
So you ended up using only the 1 year after the intervention, right? For this.
Yeah.
Oh, okay. But same for the segmented regression or not?
No, for segmented regression, I just choose the outcome variable to be monthly TBI deaths and the exposure to be CPG intervention, and then control with time.
But what I mean is the the whole period of data collection. Did you use it for the segmented regression?
Yeah, for all period of data collection from 2013 to 2022. But here is only from 2015 to 2017. This is the
I see.
chosen time.
I
Yeah.
see. Oh. Alexander shared earlier in the chat as well. Because there is construction background. It's not as well defined. He says that there is a video model that can be used in the joint form projection, which is made available by the NIH as well. It's probably very similar to the segmented Poisson regression to study for anyone. But if anyone is interested, you can look online for joint form regression.
So, Joao, what was the comment there? I don't get it from the Alexandra. Can you transcribe it, translating it?
He says that if anyone is interested, there is a model called joint point regression that is made
Okay.
available by the NIH as a video, a tutorial video. So if you want to search on YouTube or Google for joint point regression,
Okay. Okay.
I think it's joint point regression. It's gonna be pretty similar to the segmented model. Yeah.
Okay, so he's recommending maybe you can also use that to do the same thing, right?
Yeah. But I think it's gonna be very similar. It's a linear model.
Okay.
All right. I think that's it. If anyone has other questions, I'm sure that Timot is open to respond. Timot, please share the slides with Leticia as well so we can have them saved for the future. And